Every summer, every other summer, like clockwork, I get bit by a spider, and then I swell up my legs swell up like a pumpkin. So it's that time again. So it may or may not stand up too much. But anyway, today we're going to be looking at 3.2, and it's kind of in general seeing how some of these things work, and then we're supposed to do 3.1 today. We're a little ahead, sort of, not really, kind of. I don't know where we are. Going to this 2-day-a-week thing is kind of messing up my schedule, but it does say tentative, so whatever. Okay. I feel like we're making pretty good time, and I think we're doing okay in terms of, like, people seem to be catching on, so it doesn't seem horrible. So I don't feel like we're going too fast or anything. It seems like it's the normal flow of things. Just, it's a good flow. I'm not sure it's normal because I've never done a 2-day class of this before, so it's a little weird getting used to, but whatever. Anyway, so in 3.2, and as we say, we'll kind of hit 3.2, and we'll kind of talk more about what we talked about last time and flesh out some more of the answers too when we get there. But this is all about your solutions to a, and then last time we were doing second order linear differential equations, but in order linear differential equations. Okay, and the whole point of this is that when you have a situation like this, you know, we'll start off with the second one, something like this, something along these lines. Remember, this is homogeneous because it equals 0. Homogeneous, something along those lines. Homogeneous because it equals 0. Okay. And the game here is this, is when you're all done, you will add a solution that looks something like this. C1 y1 plus C2 y2, something along that line. And the idea between those is, we talked about last time, because it's of this format, we know that our y's will always have the format, will always be some e to the RT, right? So we did this last time, we solved them out. And we had 2 solutions because it was a second order, okay? But if it was a third order, you'd have 3. If it was a fourth order, you'd have 4, and so on and so on and so on. That seems pretty straightforward. And they will all be of this fashion like this. And we call this a linear combination. This is a linear combination. Linear because, notice we didn't do anything with the y's. They're just y and y. So it's y to the first power and y to the first power. Linear combination. A linear combination just says you multiply by any coefficients, so these C1s and C2s. We're not multiplying by anything with y, with the x or t's or y's or anything else. It's just a number like 6 or 12 or 22/3 or whatever it happens to be. Okay? Our answers will always be of that fashion. Always. So in the case of a second order, it looks like that. In the case of a third order, it would look something like this. It'd always be of the format C1 y1, C2 y2, C3 y3. We mentioned that last week. So it'll always be like that. It'll always continue out like that. The question, though, becomes this, and I mentioned it last week briefly, is that these guys here need to be linearly independent from one another. Okay? Now, what does that mean? It means that I don't want it to ever be a situation where if I multiply this one by like 7, this one say by 2, and then add it all together, it goes to 0. Okay? If that were true, if you could multiply this one by this constant and this one by this constant, and then add them up and it would drop off and go to 0, then in essence they're the same solution. Okay? So what we're going to talk about today is this, is we're going to look at some solutions and see if they are or are not independent. There's a quick way to do that. And then we're going to get more into the actual solving of these guys. Okay, they'll always be of this format. So then, of course, how do I find these C1s and C2s? Well, in the case of a second order, I'm going to have to know y of something, like y of 0 equals something, and y prime of something equals 0. Here I have 1, 2, 3 missing terms. It's because it's the third derivative, so I'm going to need to know y of 0, y prime of 0, and y double prime of 0, for instance. I'd have to know those in order to find these 3 missing coefficients coming out of here. Okay, so if it's just like a separable, If this is a separable first order, I just need, y of 0 equals whatever. There's one constant missing, I need one value. If it's a second order, I'm going to need 2 initial conditions. If it's a third order, I'm going to need 3 initial conditions, and so on and so on and so forth. Okay? Pattern will always hold true. Okay, so you may recall last week we did one of these, and let's just start off with a couple of these just for fun and see what happens. So if you had this guy, and we'll start off with a nice easy one because it feels like Monday, but it's not really Monday. It just feels like it. Plus 5y equals 0. We know that our equations are always of this format. Okay, and because they all have an e to the rt, I don't need to include them, so this will just become r squared plus 6r plus 5 equals 0. That's r plus 5, r plus 1. So -1, positive, or -1, -5 are my two answers. So my solution will be of the format y equals c1 e to the negative t plus c2 e to the negative 5t. Okay? And that's what we did last week. We did that a couple times. We're going to look more into that today. But here's the question. Can you find any constant that you can multiply this one by, and any constant you can multiply this one by, but constants like 5 or 2 or 12, such that these guys would add up and go to 0? No, because e to the negative t is grossly different than e to the negative 5t, yes? They are linearly independent. And because they are, this is a perfectly good solution. Okay? If they aren't, then we need something else to happen. Okay? So in the case of these guys, this particular solution will always work. Okay? It'll always work in this particular case. Once in a while, someone will say to you, hey, is it possible that these things are, is it possible that they are solutions? I don't know, but I can check them and see. Okay? And so they may, like individually they may check, yep, that would work. Yep, that would work. Yep, that would work individually. That is, each one of them, if you take the derivative of this guy repeatedly, you'll get this, 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 and this. If you plug them into this guy here, this one will work by itself. This guy will also work by itself. Okay? But they must be linearly independent for it to actually be a solution. Okay? So again, let's just run through that real quick. If you took this C1 right here, if you took this piece right here, and you took the derivative of it, what would you get? Well, you would get negative C1 e to the negative t. And if you took the second derivative, you would get C1 e to the negative t. And so if you follow the recipe up here, the recipe says to take the second derivative, so C1 e to the negative t, plus 6 times the first derivative, plus 5 times the original function. And what happens? Well, you get 5 plus 1 is 6. And then this, of course, becomes minus 6. And lo and behold, it equals 0. In other words, that is a solution in and of itself. This guy here works by itself. This guy here will also work by itself. And they also work together. And they can work together because they are linearly independent. Okay? Later on, we'll see ones where this, like that piece would work by itself. This piece would work by itself. But in fact, those two functions may be not linearly independent. So they cannot be together a solution to this problem. Okay? And so just kind of keep that in mind as we go through. Again, that original equation up there, that's why does that look funny? Let's come back up here. Oh no, because I got 2 double primes. There. It looked funny. That's because it was funny. Yeah. Okay. So again, we're going to be checking some of those today. Be aware that throughout, if you're doing this solution, you will get this little bit here that we just did over here. This will always produce good answers with the exception of one case, which we're going to look at in just a minute, which you talked about last week a little bit. Okay? So let's try another one of them. Suppose this is the one I talked about last week when we did these. I think it was this guy. And again, so that's going to be r squared plus 6r plus 9. So that's r plus 3, r plus 3. So the answer is negative 3. It's a double root. Here's our problem. This cannot be our solution. The way I'm writing it right here, this cannot be our solution because those guys are clearly the same. Okay? When you can multiply this by something and this by something and add them together and get them to go to 0. The fact that this can happen means this isn't our answer. This is not our answer here. Okay? Because they are not linearly independent. This is straightforward and obvious on this one, right? Later on there'll be some that's not obvious just staring at them, okay? Although most of them you could probably take a wild stab and go, yeah, but that one is, no, probably not, yeah, probably, yes, maybe, probably not. But these ones here, they're basically, they are the same function. E to the negative 3t is the same in both cases. The only difference would be that constant. And by the way, it looks stupid to write it like this because wouldn't you just rewrite that as c1 plus c2, parentheses, e to the negative 3t. In reality, what is c1 plus c2? It's just a constant, isn't it? And so it's going to go away. Okay, so this case here, it's not linearly independent. So if you remember last week, what did we say when that happens? We do c1 plus c2 t times e to the negative 3t. That's how we got around that. And in fact, what you'll end up with is c1 e to the negative 3t plus c2 t e to the negative 3t. And now, if you look at this, is there any way that you can multiply this by a constant and this by a constant and get them to cancel out? Provided that they're both not zeros. If they're both zeros, then yes, you can. So is there any non-zeros constants you can multiply by to get them to go away? No. That's because they are linearly independent now. Okay? That is a big deal. Without linear independence, it will not work. Okay? It will not work. So then the question then simply comes, how do we test them out? Because these ones here, they were pretty straightforward and obvious. But if you were given some ideas, how would you go about testing them? And so the way to do that, and this is one that I never do these off the top of my head because I just mess them up. It's hard. It's not hard. Well, is it hard? Yeah, it's hard. Person could sit down and come up with someone that would work, but it's too much trouble. So I just looked them up in the book and just go, I'm going to go that way. Cool. Okay. So here are some examples of some solutions, and they want you to know if they're linearly independent, yes or no. And so if you had this situation here, where you had, and your book just at this point just gives you, they just call them f of x, g of x, and h of x. Oh yeah. And h is 3 cosine squared. Okay. So the question is it possible that these things here are some solution to an equation that looks something like this? Well, I'll write it with f of x, g of x. Is it possible, this is what our question is it possible we have a situation that looks like this when we're all done? Or is it possible that this guy here, oops, that's a plus sign. Is it possible that we have what we have? Is it possible that they are linearly independent, yes or no? And if not, how do we go about proving that? Okay, that's what I want to know. So, is it possible we have this situation? Okay. Well, in order for us to know that, the way we prove that is to say that we need to know, does this thing equal 0? Is there a possible way that I could make this thing equal 0 by multiplying by C1, C2, and C3, adding them together, getting them to go to 0? Okay? Now, in this particular case, I guess I changed my method. I'm going to put the 16 back in here. I started to go with F and G and H, and then I changed my mind. Okay, there we go. I'll just write like that. I think it's pretty clear. On this one that if I multiply this one by 0, which I can do this, I can multiply this guy by 0. Nothing wrong with that per se. They can't all be 0. So this one could be 0, yes? If this were 0, then this could be, for instance, let's see, I'm not going to deal with fractions today. I could do this one by 3. Probably, yeah. I could monkey. Point is, I could monkey around this thing. I could probably make it go away. Okay? If I sat here long enough, I could probably make it work out. Maybe I actually don't want that to be 0. Maybe I want this to be, -8. Yeah. Positive, no, not -8. Positive 8. Positive 8. Positive 8/3. Yeah. Yeah. Now you're like, do I have to do this at home? No, you don't. Just watch carefully. So I'm going to go this times by 8. That's going to be 16. Oh, I wanted 16/3 here. Yeah, 16/3. There you go. Yeah, sine squared. That's cool. Plus 16 times 16/3 times 3 is 16 cosine squared. Oh, that's hot. Nice. Nice. And of course, hey, I know what that is. This is 16 sine squared plus cosine squared, which is 1, yes? Which means it's just 16. So what would I want to multiply this by? -1. Yeah! Sweet. Nice. And so because that can happen, because I can pull that off, that says that these guys are not independent. That make sense? Because I can do that, these guys are not independent. Now, if you're going, this brings back shades of algebra that I hated and I'm trying to forget about. I'm right there with you. There's a faster, better, easier way. Okay? But this is what we're trying to show. Okay? And so it's one of those deals where you started in one way and you're like, no, that was dumb. Somebody else might have said, wait, cosine squared is 1 minus sine squared. You could replace that here, done some monkeying around. You'd have gotten there eventually. Probably. Okay? But that would work. But because, again, because it equals 0, they are not linearly independent. You could say they're linearly dependent if you prefer. Okay? Doesn't make any difference to me how you phrase it. Now, how do I go about proving that faster without having to do any algebra? I'm glad you asked. So we're going to use what is called the Wronskian determinant. It is the easiest thing you will ever do. I don't know about that. It's pretty easy though. In the case of it, it'll always be an n by n. I'll start off with the matrix, then we'll find the determinant of this matrix in a minute. Okay, it'll always be n by n. So in this case, we had 3 equations. So the top row in this case, so it's going to be 3 here. So we're going to have f, g, and h. And then what we're going to do is we need to have 3 rows as well. So it's going to be f prime, g prime, h prime, and then f double prime, g double prime, h double prime. And then we're going to take the determinant of this thing. So it's in this case, it's a 3 by 3. So if I simply find the determinant of this matrix, and again we show determinant like this. If we find the determinant of this guy, the question is if equals 0, okay? If equal to 0, they are not independent, or if you prefer, they are dependent. So less algebra in a lot of respects this way, and we're going to actually automate this skosh because I hate screwing around with a bunch. Well, okay. No, I don't mind telling you this. I don't really enjoy doing determinants by hand. Oh, I don't know. I really don't. It's not that much fun. I will do a couple of them just to kind of show you that I can, because you know you should know that you have a teacher that can do matrices, I guess. Whatever, dude. And then I'm going to show you how to automate the process a little bit. Okay. So in our case, we had. Oh, what was our top row? It was 16. Was it 2 cosine? 2 cosine squared? 2 sine squared. And then 3 cosine squared. Nice. So the derivative of 16 is 0. Second derivative is also 0, so that's handy. Ugh. All right. What is the derivative of 2 sine squared?
2 sine 2x.
2 sine 2x. Well.
Or 4 sine 2x.
So it's,
No, no,
well, okay. So some people are a little fancier than the rest of us. Okay. So this is been a while for some of us, maybe. Remember, the 2 sine squared is really this, right? Okay. It's been a while for some of us. Yes. And so you bring that down, so it's 4 sine x to the first power, of course, yes? But times the derivative of the inside, which is cosine. And then this is totally legit way of writing it. If you remember, and again, this plus $1 gets you a coffee at McDonald's, so I don't really care if you remember it. It's kind of nice and handy. This right here is what?
Sine 2x.
Sine 2x. So this is 2 sine 2x. That's nice. If you can remember that off the top of your head, God bless you. I can't. Right? I would have just done it out, and then I wouldn't have gone from here to try to come to right here. Good for you. I would have gone here to here to here. Maybe rewrite it. Maybe leave it alone, because I'm going to do another derivative here in a minute, anyways. So it's going to be 2 sine 2x. Okay. What about this next one here? Come back here. All right. 3 cosine of square root of x. Oop. So it's going to be 6. That's a terrible pen. 6 cosine x times negative sine x, which looks like negative 3. Oh, well, I'm going to write negative 6 first. Sine x cosine x. Hey, that's sine x cosine x. I can pull a 2 with that, so it's going to get negative 3, 2 sine x cosine x, which means I have negative 3 sine of 2x, yeah? Is that true? All right. I guess I'll do this one next because it's already here. Negative 3 sine of 2x. All right, what's the derivative of that?
Negative 6 cosine 2x.
So negative, so it's negative, I'll write like this, 3 cosine of 2x times 2, is that right? Right, chain rule?
Yep.
And so it's negative 6 cosine 2x. Negative 6 cosine 2x. And this one's going to be 4 cosine 2x. Or it should be anyways, right? By the same basic procedure. All right. Now, if it's been a while, how do you take the derivative, how do you take the determinant of a 3 by 3? And I know I will not be doing that augmented, draw the lines, and I don't do that method, all right? So what's the other method by hand? The expansion by minors. Remember playing that game back in the day? If you do not, fear not. I will give you a couple of examples, and I'm recording because Avi is not here, and maybe 2 people are missing today. I don't know, whatever. Whatever, I'm going to put it online. You can watch me do it again if you want. So expansion by minors. And typically, I use the top row, and I'll show you that, but you can actually use any row or any column. And if it was me, I would probably use the first column because it's going to be way less work than screwing around, okay? But I will show you how it works. So let's say I pick this top row, then I'm going to do 16, and then what I do is I cross out its row and its column, and whatever's left is going to be this little tiny determinant, which we call a minor. That's why it's called expansion by minors. There's so many ways to do these things. Well, no, so many ways. There's several ways to do these. I find it very off-putting to do the other two augmented ones and then multiply and multiply. And I don't know. My son, when he went to college his first year, calls me, or he comes home, he's like, "This crap's so hard." I forget what he's doing. I think he was doing linear algebra or whatever. But they're talking about determinants. No, they're talking about something about determinants. Oh, cross products, which are just determinants. And he's like, and like the teacher just made him memorize this formula. I'm like, oh, for God's sakes, it's ridiculous. So just draw it out and learn how to do it the right way. But whatever. Notice that the next one is always minus. It's always minus. So it's minus this top guy here. And if you cross out his row and his column, you get 0, 0, and these guys here. So this one actually isn't too bad. If you just use the top row, but you can actually use the first column, or the first column as well if you like. That'll actually be really easy too. 0, 0. And then plus 3 cosine squared x. And then if you cross out his row and his column, you get 0, 0, 2 sine 2x, and 4 cosine 2x. Nice. All right. So how do you do the determinant of a 2 by 2? We just cross multiply like so, yes? Minus this times this. And so I'll start with the easy ones. 0, 0. So this garbage over here is all 0. Now here, I'm going to get negative 12. Oops. Negative 12. And then it's going to be sine 2x, cosine 2x. I'll just leave it like that. And it's going to be, and it's always, remember, it's always minus. It's always minus. Minus, and then it's going to be minus 12 again. Sine 2x, cosine 2x. So minus and a positive 12 cancel out. Yay, it equals 0. The fact that it equals 0 tells me that these solutions were dependent, or they're, if you want to say it, not independent, whichever makes you happy. Okay? Not too terribly difficult. I don't think, anyways. I hope.
Do we need to know how to reduce like 4x4 matrices?
No.
Okay.
Now, I will do this one and by the next one I'll do them by hand, both, but then I'm also going to show you how to do them on calculators because it's just so much better. And honestly, you don't do a ton of this. This is just a deal where if someone wants to know if it is a way of showing that these functions are independent. Okay, that's a very big deal. You need to understand things are independent. That said, all the solutions that we will be doing to the problems that we're doing are not in this particular section, but I mean in the actual solving of these problems, they're all going to be independent. Okay, the only ones that aren't are the repeated root problems, and on the repeated root problems, we'll be actually using that method I showed you a minute ago to produce independent functions. Okay, so if you have your calculator, pop that baby out real quick. The TI-89. If you want to use the emulator, that's fine. And we'll put that thing through its paces a little bit. Nice. So what I normally do, and you can do it a couple of different ways. I don't like to use the same. I don't like to type in the function 87 times. Does that make sense? So what I'm going to do is I'm going to store things. So I'm just going to go 16 like that, and then the store key is right here. So stow, and then just alpha A is what I'm going to do. So just stow alpha A, enter. Should say that. And then I'm going to do, what was the next one? 2 times parentheses sine of x squared. And then stow alpha b, like that. And then 3 times parentheses cosine of x squared stow alpha c. Nice. Once you get them stored in there as those variables, you won't have to type them in again. That'll help you out a little bit later on. Okay? Again, on the test, I won't give you anyone that's so nasty that a person couldn't do it by hand, but let's be honest. Yeah. That took, I don't know. I could have done that expansion by minors probably a little faster, and that one had a bunch of zeros. And if it didn't have zeros in it, that would have probably gotten a really messy problem for S. It would have gotten messy pretty quickly. The fact that this had a constant, so we had zeros and zeros, that really made my life easier, / probably too easy. So I'm probably not going to worry about that too much. All right. So the matrix button, the matrix brackets are here on top of the comma and top of the division sign. So if you hit that, if you've never used 89 for matrices, you have to open the matrix, and then the notation is top row separated by commas. So we're going to go A, comma B, comma C, and then we're going to go semicolon. Semicolon gives you the next row, and then we'll go from there. So just alpha A, comma, alpha A, comma, alpha B, comma, alpha C, and then the semicolons on top of the 9. So then for the second row, the formula is going to be similar, except we're going to take the derivative of A with respect to t, comma, the derivative of B with respect to t, comma, the derivative of C with respect to t. So to do that, if you hit F3 for calculus, differentiate, and it's just A, comma, t.
You did the variables in terms of x.
Thank you. That would be a problem. Glad someone's paying attention to me. Comma, differentiate B, comma, x, comma, differentiate alpha C, comma, x. Semicolon. And then the third row is your second derivatives. So it's going to be, it should be x. So A, comma, x, comma, 2, B, comma, x, comma, 2, C, comma, x, comma, 2. Bracket. So once you learn how to do this, you can do this so much faster, and you get to the gist of the matter, which is the important part. Don't forget your comma, though. That's a problem. Comma, differentiate B, comma, x, comma, 2, differentiate C, comma, x, comma, 2, bracket, hit enter. And there is our matrix. Notice that it looks different than ours. That's because the computer didn't simplify it and pretty it up like we've simplified it and prettied it up, but they have the same value. This is an in-between step, so please don't, in the middle of it, think that you screwed up. Lots of ways to get somewhere, but the in-between steps don't always look the same. Okay? So the question is simply this: when we're down here in a minute, take the determinant of this thing. Will I get 0? That's the question. Okay. Everybody typed in? If you didn't, let me know. Well, you engineering people should be able to run this calculator. Like I can do it. I can do it. I'm not that bright. Okay? So then, to do this determinant, a couple places to find it, but the best place to find it is under math. So second F5 or second number 5. So if you go second number 5, you will see matrix, and we're looking for the determinant of, and then we're just going to click this matrix in there, and I'll show you what I want to do by that. Okay? So second number 5, and number 4 is matrix, and determinant is number 2. So I'm going to take the determinant and then just arrow up and click on this guy, hit enter, close your parentheses, hit enter, and don't screw it up. Yay, it equals 0. Nice. Did it work? No?
Yeah, we got it.
Good. Did it work? Yeah.
I gotta step back.
All right.
That's fine.
You good? All right. You're just gonna do it all by hand, huh?
Yeah.
All right.
I have an emulator on my laptop. I'm just not using it.
Is he fine? I'm proud that you can do all that derivatives in your head. I can't. What was this up to? For which one?
Just the last part.
So second. So escape. So second. Second. And 5.
Second before.
Yep. Determinant, arrow, grab it, and push parentheses. There. Yay.
0.
Did it work?
Well, that's good.
What do you got?
This way.
Oh, it's good. Okay, so you. Okay, I'll do it. Okay, watch this next one. Okay, I'll do this next one by hand again, and I don't care if you do it by hand or on the computer, right? Some of us, it's been a while as far as derivatives, as far as the algebra, as far as everything else. Getting lost and not getting 0 is not okay. Okay, that's a problem. If you cannot show that these are dependent or independent, that's not okay. So find a way that works for you. Okay. Some of you will find that taking the derivatives is the hard part. Fine. Take the derivative on a calculator and draw it on your paper. Okay, that's totally fine. Okay, and then do the determinant by hand if you want to do it that way. Good for you. Okay, so I'll kind of try to show a hodgepodge of which one. Hopefully somebody likes this one. Hopefully somebody likes that one. Whatever. The goal is to get the right answer. Okay, so we'll see what happens. Let's try this one here. X. Oh, nice. So if you have f of x is x, g of x is the cosine of the ln of x. Oh, that's disturbing. Is that right? Yes. And then h of x is the sine of the ln of x. Of course, x bigger than 0. Otherwise, we're screwed. I don't know. Well, let's take derivatives by hand for fun. Let's do that first, I guess. So f prime of x is 1. F double prime is 0. What's g prime going to be? It's going to be negative the sine of the ln of x times 1 over x, yes? I think. Now, it's at this point that I'm like, I don't know. I mean, yeah, in theory I can do that by hand. I'm not going to do that by hand. So I'm going to bring up my calculator and have it help me. So just take the derivative of the cosine of the ln of x with respect to x. And so that's what I got. Good for me. And then just come back into that parenthesis and put comma 2. And there's your second derivative. So sine of ln over x squared and then minus cosine of ln over x squared. But this other one's going to be kind of close, huh? So the other one here is going to be, right, the other one is going to be the cosine of ln times 1 over x. And then if I was a betting man, I'd say it'd be the same, but with a plus sign, but let's just double check it. Nope, I was wrong. They're both negative. Interesting. It's a negative cosine of ln over x squared minus the sine of the ln over x squared. Okay. Awesome. All right, so I'll try to write them off to the side of the board over here so I can look at them while I'm typing them back in again. So when we do these, I guess a big sheet of paper if you're doing it by hand. A big sheet of paper and a lot of luck. Okay. Now again, you're free to use any row or any column. The nice thing if you use first column, if you use the first column, it's going to be x times, now it's going to be x times this guy right here because it's the only one that x is not in. It's going to be this minor here. If you use 1, it's going to be the top row, what's left of the top row, and what's left of the bottom row. And if you use 0, well, it doesn't matter, right? Because 0 is going to cancel anything out anyways. If you use the top row to do it, which is totally fine, it's going to be x times this first minor. It's going to be this guy times these guys here, and it's going to be this times these guys here. But that might get messier. Okay, so it's up to you how you do it. Any row, any column will work if you don't screw it up. Okay, so sometimes I typically just use the top row every time. Unless it was a case like the last one where there was just that 1 on the top and then nothing else. In that case, I probably would have used the first row that time, the first column. But it's kind of a potato vodka deal. Just pick your poison. I think I will use, well, let's just get this down first. We're going to have x times this thing minus sine. Here's where you also make some mistakes. You'll drop stupid signs. Ask me how I know. Ridiculous. Okay. I'll do this piece first, and then I'll do the next one right below it. I guess that's the only problem. A nice whiteboard is better for this than a computer because you can have more room to work. But, oh well. All right. So if you cross multiply this guy, get this times this. Okay. Yeah. So it's going to be kind of messy. You have this times this minus this times this. So I guess we'll try it down here. So we're going to get x parentheses, and it's going to be this times this is going to be positive sine of the ln of x cosine of the ln of x over x cubed plus sine squared ln of x over x cubed. Always minus on the next one. And then it's going to be minus cosine ln x sine ln of x over x cubed. And then it's also, the next part's going to be positive cosine squared ln of x over x cubed. Oh, that's handy. So, what do you notice? I notice that this bit here cancels out. Anything else notice? The top would be 1, yes. Because sine squared plus cosine squared is 1. So you're going to get 1 over x cubed. So it's really going to be x over x cubed, which is going to be 1 over x squared. Okay? So that's for our first minor that we did. Okay? So for our second minor, I don't know that it makes a whale of a difference. Well, it's going to be gross no matter how we do it. Ugh. Yeah, I guess I'll do it this way. I don't know. I guess I'll use the top row again, because it's not that bad if you think about it, because take this top row and this middle column, then it's going to be 1 and 0 here and here. The 0 piece is going to cancel out, so I think it's not going to be that bad. I think I'll just will use that top row. So it's going to be minus, always minus cosine of ln of x times, and then it's going to be 1 and 0 and cosine ln x, and then minus cosine ln of x over x squared minus sine ln of x over x squared. Okay, so it's going to be this times this, so it's going to be just this thing here minus that, which is 0. So it's going to be negative this cosine out here times this bit here. So you're going to end up with cosine squared ln of x over x squared plus sine ln x cosine ln x over x squared. So that's my second minor. And then my third minor is going to be sine ln of x times, and then it's going to be 1 and 0 again, and then negative sine ln x over x, and then sine ln x over x squared minus cosine ln x over x squared. And when you do this, again, this piece here is going to be 0, so it's going to be just 1 times this. So in essence, it's going to be sine times this. So it's going to be the sine squared ln of x over x squared minus the sine ln x cosine ln x. What is that? Ln of x over x squared. Cool. So when you add them together, I did use the negative up here on this one, didn't I? Sure I did, right? Yes, I did. Good for me. I did something right for a change. Good for me. And so if you look at these two last minors that we have here, this piece and this piece will cancel out, correct? And then if you add those pieces together, once again, this cosine squared plus sine squared is 1. It's going to be 1 over x squared. So I already had a 1 over x squared plus 1 over x squared. Do you know what that doesn't equal ever? Never equals 0. The fact that it doesn't equal 0 shows that these things are linearly independent. There is no way that I can multiply them by constants and get them to cancel out to 0. Can't happen. Okay? I don't care what it equals, I just know that it doesn't equal 0. 0 is the magic number. If you can make it equal 0, then they're dependent. Okay? Again, not terrible to do them by hand. I think probably a little faster to do them on a calculator, probably. I think that there's a time and a place for most everything that we do in life, and I think this is another example of that. And so I'm going to go ahead and punch them in just for fun. And so if I was to do this, I'd go brackets, let's go x, comma, and then I would do the cosine of the ln of x, comma, and then I would do the sine of the ln no of x, right, semicolon. Oh, why'd you do it that way? That's stupid. Try again, Jay. Okay, let's try this again. If I'm smart, which no one's ever accused me of that. Stored as A. Sometimes I forget what I'm doing. It's my problem. I start talking too much. So it's the cosine of the ln of x. Store that as B this time. And then sine of the ln of x. Store that as C this time. There we go. Let's try this again. So, the cool thing about this is that if you were doing a bunch of these, I don't have to go do this again. I don't have to go do this again. Because up above, I already entered a matrix where I did it in terms of A, B, C. Yes? So if I just go up there and find that matrix and bring it down here, anything below this, A, B, and C will be referred to as now these functions here. Okay? So that's another reason why I think it's kind of a big deal. It's a big time saver. Right there, that's the function I want. Boom, right there. Nice. And then it's simply a matter of, as most things in life are, once you've set it up one time, everything else goes so much faster from there. And ba-boom, 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 ba-boom. 2 over x squared. But again, don't really care what it is, care that it's not 0. Okay? Because it's not 0, they are linearly independent. Okay. You guys need help on the calculators at all? Is that working for you all right? Again, if you are like the calculator for this particular thing, the calculator does not, it doesn't seem to be making things easier, it seems to be making it harder, then don't do it. Okay? Or have it take the derivatives for you and jot them down somewhere. Okay? That's totally fine. And then do the matrix by hand off to the side. Okay, that's fine. If that to you is easier, then do it. All right. What I don't want you to do is spend an hour trying to remember how to do a derivative of some gross function, which is not really the point of the class. All right. The point of the class is we need independent functions. We need to show they're independent. That's what we're talking about this. And so to do that, we need to take some derivatives. But if that requires you to, it's something that you're struggling with, then use the appropriate amount of technology to make that happen. Okay. Please, don't spin your wheels on it forever. Okay? And again, it's neither here nor there to me. I think for most of us who are, I don't know. Some people some people find calculators, computers, just way easier to do once they understand the related concept of it. And that's good for you. Some of us are like, I mean, we're old. Some of us, and Mr. Old School over here makes me feel like I'm a new school guy. But yeah, that's great. If you are fast like that, good. That actually is faster in a lot of respects, in a lot of ways. But you sometimes get too much on your mind, or you think you know what you're doing. That's the thing that always irritates me. I think I know what I'm doing, and I make a dumb mistake. Like on the first derivative too. Thank you very much. It's never like somewhere else. And everything has been blown up from there. There's way too many things depend on each step here. So again, totally up to you how you do it. Again, that's recorded for posterity. If it's equal to 0, they are not independent. And if they do equal 0, then they are. If it's equal to 0, they are not independent. They are dependent. And if it does not equal 0, then they are independent. Nice. Okay, cool. Great. Swell. All right, so here we go. I want to look at a couple of these kind of problems too. Some of these are in section 2 as well. I think they're kind of fun little problems. Now, just for fun, I'm not going to tell you what the answers are on this problem. We're going to jump in and see what happens. See what you think about it. Plus 4y prime minus 2y equals 0. Is that what I want? Yep. Nice. All right. So it's a third order linear homogeneous differential equation. It should not be y squared. That's embarrassing. You know where I was going with that. There we go. Okay? Sorry about that. There we are. Which means I can rewrite this as r cubed minus 3r squared plus 4r minus 2 equals 0, yes? Okay, how would you solve that, quote unquote, in a real world? Well, no, you wouldn't in a real world. In an Algebra 2 class, how would you solve that? Or I could graph it on a calculator, find out where it crosses the x-axis. Totally you can do that, yes? This is a cubic function. How many times does it have to cross the x-axis? It has to cross it once, right? Because the x-axis are real numbers, yes? There will be 3 solutions, yes? So they could all be real. Or there could be 1 real and 2 imaginaries, yes? So if you think about this, this is no different than an Algebra 2 class when they first taught you this, yes? There will be 3 solutions, that's a fact. But they could be 3 reals. Or it could be 1 real, 2 imaginary. That's a fact. Okay? Or, well, imaginary, let's call them complex. 2 complex, I should say. They have imaginaries, in other words. Okay, but 3 roots, regardless. That's a fact. Now, I could graph it on the calculator, and I will in a minute probably. Back in my day, we would realize that the only possible solutions would be factors of 2, yes? Right? That's kind of back how we did it back in our day. So we'd say, well, you could try plus and minus 1, plus or minus 2. That's about all you could do if they were rational numbers. Okay? I have better things to do. This one doesn't factor nicely very well, I don't think. So I'm going to go ahead and graph. I'm not going to graph on that thing. I'm going to go to Desmos. Come on, Betsy. There you go. Just a minute, we're going to update. Thank you. That's convenient. Desmos, give it to me. So what was it? X cubed? And then what was it? Minus?
Minus 3x squared
Plus?
plus 4x.
Minus 2. Nice. All right, so if you look at this guy, there is 1 real solution, yes? 1 real solution, which means the other 2 must be complex, yes? So x equals 1, or not, when we say x, we really mean r equals 1, yes? That's one of our values. Now, if you go back and look at that, well, that's nice. What that really means is that r minus 1 is times something has to equal this guy then. Right? So how would I find out what the rest of that is? Okay, I'm just going to kind of talk about this. How would I go about finding that?
Synthetic division.
You could use synthetic. I've never been a big fan of synthetic. So if you want to use synthetic, go for it. I'm going to do it the hard way with the long division, just because synthetic works. It's always confused me, even teaching it. I was like, and it only works with linear terms, which is cool, which is what I have, but I don't know. That goes into there, r squared times, that's r cubed minus r squared. So you're going to get negative 2r squared plus 4r. So r goes into negative 2r squared, negative 2r times. And that times that's negative 2r squared plus 2r. If you minus, you're going to get 2r minus 2. And that's going to go in 2 times. So this guy right here is r squared minus 2r plus 2. Okay. Now, you will not be doing this by hand today. Just be aware of what's going to, the next thing that's going to show up here. Okay, that's kind of what I want to talk about this. Right? You will not be having to do anything that I just did here, and won't do any of this business. I'm just kind of talking about this section of the book. They give you some solutions, but they didn't just pull them out of their butt. Okay, they are actual solutions that will come about because of how the thing was set up. Okay, and so here it is. If you had, now think about this. What I want to do is I want to take this baby and I want to set it equal to 0, right? So clearly it happens at 1. And it happens at wherever this guy equals 0, yes? Well, how would I find that? Well, quadratic formula comes to mind. So it'd be 2 plus or minus the square root of 4 minus 4 times 1 times 2 is 8 all over 2. So 2 plus or minus 2i over 2, or 1 plus or minus I. Those are my other r values. Right? You follow me on that one part? That feel good? Okay? Feel okay? Does it feel okay? Nice. And so now what would Euler say? My boy Euler would say, well, it's e to the I theta, right, is equal to what? He would equal what? This is cosine theta plus I sine theta. And what we're doing today, we drop the I part of it, okay? So what we're going to get here is it's going to be 2 solutions. So just pay attention to this part of it. But this is going to be 1 solution. So just going to be a cosine of theta bit here. And this piece here is going to become a sine theta. It's going to be part of its own solution. But we ignore the I part of it. Okay? Remember, we need to have 3 solutions. We have e to the t already. We already have that guy up above somewhere. We left him up there with the 1. And I need 2 more solutions. Okay? So one of them's going to be with the cosine piece. One of them's going to be with the sine piece. And so the I just says this piece with the I is going to be one of our solutions, and we drop the I. And the piece with the cosine without the I is going to be our other solution. That gives us our 1, 2, 3 solutions that we were searching for. Okay? That's a big deal. That's how we determine our different solutions. There's a piece that's the real piece and the quote-unquote imaginary piece. Remember, imaginary worked well when the Greeks back in the day, supposedly, we're trying to find out the dimensions of the square of the square that would fit in their that would take their rectangle and make it into their square. Hey, I can't do it. Oh no, it's imaginary. Oh, okay, that made sense to think of it like that. However, as you engineering types know, reach in, fish around, and grab some stuff inside of an electrical component. It could very well be an imaginary current that kills you. Okay, or gives you a bite. Okay. Because it just determines direction. That's all that matters inside in that case. So don't freak out about it. Don't take that literally. We've always I think people do a piss poor job of teaching complex numbers. No, it's imaginary. Isn't that nice? And then kids always go, well, if it's imaginary, why are we looking at it? Now, well, it's a good question. I don't know. Okay. Now, the difference today is this: is we are going to be looking at. Well, I'm going to leave that there. I'm going to bring this down and go one step further. So if I have e to the a plus bi theta, like so, and I should actually write it like this more. I should write it more like this. A plus bi theta. I'm going to have e to the a. Well, we already know how to deal with e to the a. We've had e to the a forever. Times e to the bi theta. Well, it's technically going to be b theta. But that's the idea that when I look at this deal here, this piece here is just going to be some e to the whatever function. In our case, it's going to be e to the t, right? Because we had a 1 right here. And then we had plus or minus I, 1i. So this is going to be times cosine of t plus I sine t. And when we're all done, we are going to get 2 solutions out of this. We're going to get e to the t cosine of t plus e to the t sine of t. Okay? So the idea here is our original equation way up there, whichever I lost it at, way the heck up here. Where did it go? Oh, that was right there, is going to be, our final solution for that is going to be y equals, it's going to be C1 e to the t, from way up above, yes? When t was equal to 1 earlier, yes? When r equaled 1. Plus C2 e to the t cosine of t, plus C3 e to the t sine of t. Okay? That's where we'll end up going with these guys. Okay? Now, good news. This is not how this problem was phrased in the book. Allow me to demonstrate how this problem was phrased. This will be our answer as far as we're gone. We've not finished this problem yet. Okay? But originally in the problem, you know what it said? It says, here's this equation, y triple prime plus y double prime plus y prime, yada, 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 right? And then it says this, show, it says this, and 3 linearly independent solutions are given. Cool. You know what they are given? Check it out. E to the x, we use e to the t, but whatever. E to the x cosine of x, nice. And e to the x sine x. I'll be dang. Nice. And they said those are 3 linearly independent. Here's a question. Is e to the t cosine of t, e to the t sine of t, are they linearly independent? We're going to go check that out in a minute, okay? The book said they are, but how could we prove that? Number 1, okay? Number 2, we solved this and found these pieces ourselves. The book gives them to you in this section, okay? How did they get them? The same way we did, okay? And then the question is, how do I find these C1, C2, and C3s? Well, I need to know some initial conditions, yes? And they are y of 0 equals 1, y of 0 equals 1. And this book, and many books like it, do this next step, and it just really annoys the bejesus out of me. It says that. And there aren't too many things that I get really weirded out about and really anal about. That's one of them. That makes me want to punch somebody, okay? This says that my acceleration and my velocity are the same. No, they're not. They might be both 0, but first derivatives and second derivatives are not the same thing, okay? They may have the same numerical value, but from a physics standpoint, that really pisses me off. Okay, just saying, okay? There aren't too many things that I get weirded out about like that. Most things I'm like, whatever, dude. That's about one or 3 things I can think of that I just want to hit somebody when I see that. It drives me a little bananas, okay? Now, how in the devil would we find C1, C2, and C3? How do we do it? Well, we plug them in. So what would happen here if you plugged 0 into these guys? Well, you would get, if you plug 0 in, you would find that it's supposed to equal 1. So if you plug 0 into here, you would just get C1. That's handy. This would be 1. This would be 1, so you get plus C2. Oh, gross. 1 and 0 is 0. Okay, so there's that. Okay. So there's your first equation. We're going to need 3 equations. We're going to need to know what y prime is as well. So what would y prime be? Well, it would be C1 e to the t. It would be C2 e to the t cosine of t, because it's a product rule, plus, it's actually going to be minus, C2 e to the t sine t. That's for this guy here. Plus C3 e to the t sine t plus C3 e to the t cosine of t. And at 0, all your signs are going to go away. See, what's that?
What about a constant?
Well, it's 0 times this is 0, yes. Right? So these pieces are going to go away. So then this is going to be C1 plus C2 plus C3 equals 0. See, the side of me that wants to make my life easier wants to combine the sines and cosine pieces. So I think I'm going to, before I take the next derivative, okay? Oops, y prime, I mean. So C1 e to the t. So let's look at our cosines. I got a cosine here and a cosine here. So I've got C2 plus C3 e to the t cosines. And then plus, and then I've got a C3 minus a C2 e to the t sine t. And all I did was just combine my like terms to maybe make my life easier, or maybe makes it worse, I don't know. So y double prime would be C1 e to the t. That's going to be C2 plus C3 e to the t cosine minus C2 plus C3 e to the t sine plus C3 minus C2 e to the t sine plus C3 plus minus C2 e to the t cosine t. Again, your sines go away. So you're going to get C1 plus C2 plus C3 plus C3 minus C2 equals 0 from above. We said that. So then you're going to get C1 plus 2 C3s equals 0. And where's the other one? C1 plus C2 equals 1. Yay! How exciting, huh? You're dying, you know. Could I do this in my calculator? Would it be easier? I don't know. Yeah, there's a lot of moving parts and pieces though, but yeah, in general it's easier, okay? So obviously you get down to here. This one's nice because it's so beautiful. Here's C1 and C2, here's C1 and C2. C1 plus C2 is 1, cool. That means that C3 must equal negative 1 then, yes? So if you just go 1 plus C3 equals 0, C3 must be equal to negative 1. Well, if you plug that into there, you're gonna get C1 plus minus 2 equals 0, so C1 is equal to 2. And then, so then I guess C2 must be negative 1 then, right? Because that makes 1. So then my final answer then would be 2 e to the t, and then minus e to the t cosine t, plus, not plus, minus e to the t sine t. That should be my answer. Messy. The fact that it's a book problem and then all the answers come out with nice integer values, you're probably right. I've always wanted to write a book. Well, that's not true. I've always dreamed of writing. No, that's not true. I've often thought about it would be cool if you could write a book and have every answer in the book be not a real, not a whole number. Nothing comes out with an integer value. Everything comes out of the fraction decimal. Nasty. And not a nice fraction even. None of this 0.5 crap. All right? Everything would come out just gross. You'd be like, no! Yes, the real world's messy friend. Yeah, I don't know. But you get lulled into this idea that everything factors, everything has a pretty answer. Oh, isn't that neato? No, it's not. No, it's not. We like weirdness sometimes. Yeah, so there's our answer. I guess a couple of things I'd like to look at is, does that seem reasonable? Let's graph this answer down here, shall we? Let's just see what that looks like on the old Desmos. See if Desmos agrees with us. So what did I say? 2 e to the t, or e to the x rather, e to the x. And then what? Oops, no. X. Cool. And then what? Minus e to the x times the cosine of x minus e to the x times the sine of x. Oh, nice. All right, question. What was the value at y equal at y of 0? What was the value supposed to be?
1, 1.
Nice. What was the slope supposed to be right here?
0.
Oh, it is. The second derivative was also 0, by the way. First and second derivatives are not the same. But the second derivative is also supposed to be 0. Which second derivative means there was a change in concavity, yes? Good, friends. I feel like that's probably our correct answer, right? Nice. I like it when it happens that way. This function right here describes what was seen in the previous problem, okay? Now, again, I did this problem the long way for two reasons. Was to show you where those things come about, to show you that we had linear independence. I didn't prove that yet. I'm going to prove that momentarily, okay? And to see that yes, we can solve these problems out, and it's not terribly, horribly, awfully difficult to get here, okay? How would I show those are linearly independent, though, our final values? Our final values, and I don't want to use our final values. I just want to use e to the t. I want to use e to the t cosine of t and e to the t sine of t. Remembering that I could put any linear combination in front of them, any constants in front of them, and I cannot have it equal 0, yes? So how would I prove it? Well, I take derivatives, yes? So e to the t, e to the t, e to the t, cosine t minus e to the t sine t, and then e to the t sine plus e to the t cosine. This is what we just did a minute ago in the determinant. E to the t, this is the same as this, so this first part stays the same. And then the derivative of e to the t sine t is literally right here, yes? Right? But I'm just going to throw a negative in front of it because this is a negative of that. Minus e to the t sine t minus e to the t cosine of t. And then this one, take the derivative of this guy, e to the t sine is itself. I mean, this thing right here is the derivative of that. So it's the derivative of that. So e to the t sine t, e to the t cosine t, plus the derivative of this thing, which is that guy right there. Cool. So notice here that our e to the t cosines cancel off. So I really just end up with 2 e to the t sine t. And the same thing is true over here. I get 2 e to the t cosine of t for my second derivative. Ugh. This is gross no matter how you slice it, I guess. I'm going to do it up here. Again, just practicing this idea that are they independent, yes or no. I already knew they were going to be because of how we got to them, okay? But if I didn't come at it from that point of view, I'm not sure they're independent, this is how I would check them, okay? So I'm going to take e to the t, and that middle guy, e to the t cosine t minus e to the t sine t, and then e to the t sine t plus e to the t cosine t, and then negative 2 e to the t sine t, 2 e to the t cosine t, and then minus always. I guess I'll go. Yeah, I'm going across. I guess I'll go across the top. So minus e to the t cosine t, and then e to the t, e to the t, e to the t sine t, t cosine t. Where did I leave off? 2 e to the t cosine t plus e to the t sine t, and then e to the t, e to the t, and e to the t cosine t, minus e to the t sine t, minus 2 e to the t sine t. Ugh. All right. Ugh. E to the t. Yeah. Ugh. I don't care anymore. Does everybody have an e to the t? Everybody has an e to the t, yes? I'm going to pull that all out of everybody. Just going to factor that out of everyone. No, I'm not. Just leave it in there. Don't be lazy. God, you're lazy. All right. Let's see. This times this is going to be, yuck, 2 e to the 2t cosine squared t minus 2 e to the 2t sine t cosine t minus, it's already a minus though, so plus 2 e to the 2t sine t, sine squared t rather, plus 2 e to the 2t sine t cosine t. That's gross, but they cancel out, so that's handy. And so then this times this plus this, nice. So it's e to the t. You can factor 2 e to the t out of them, and you get cosine squared plus sine squared, right? Yes? Everyone happy with that? So then it just becomes that bit right there, which is handy. Let's do this guy here. So it's 2 e to the 2t cosine t minus e to the 2t sine t minus e to the 2t cosine t minus e to the t cosine t. And sure, I get cosine, I get e to the 2t cosine t minus e to the 2t sine t so it's going to be minus e to the 3t cosine squared t plus e to the 3t cosine t sine t. I'll write that over here. You're like, I don't see how you're going to get 0 on this. Me either, which is good, because I'm not supposed to get 0 on this one, right? So sometimes you get lost in some of this stuff. You get too close to the forest, you can't see the trees, kind of a deal. You're like, it's never going to cancel out. I hope not, because they're independent. Okay, so don't freak out about that. What does it have to equal? Not 0. There's a lot of stuff that isn't 0. Some of it's really messy. Okay? And then this next deal over here is going to be very similar. So it's going to be minus 2 e to the 2t sine t minus e to the 2t cosine t minus plus actually e to the 2t sine t. So if you distribute that, you get negative 2 e to the 3t sine squared t. Oh, it's actually going to be positive 1 because there's 2 of them here and 1 of them there. I didn't catch that. No, it's going to be negative 1. And then it's going to be minus e to the 3t sine t cosine t. What? Sine, wait, what? Sine t.
Sine squared.
Oh, sine squared. I was like, where'd the 2 come from? Sine squared of t. There you go. Minus e to the 3t sine t cosine t. And these guys cancel out. And you can clean this up a little bit more if it makes you happy. This would be 2e to the 3t here. And then you could pull out a negative e to the 3t here, and you'd be left with cosine squared plus sine squared, which is 1. So you end up with e to the 3t. But again, it's not 0. Okay, it's not 0. The fact that it's not 0, they are not, or they are independent. They're not dependent solutions. Okay? Questions on him? Not too bad, huh? What's the matter? Where'd you leave you? Where'd I lose you? Can't read my ugly handwriting, can you?
I
So-
think that is a class product.
It is. Oh, yes. Yes, a cross product is a determinant. You're right, exactly. 100% correct. Exactly. Yeah, that's what I was saying earlier about my son when he first learned how to do cross product. The guy didn't explain that. It's like, this is how you get, it's like AB minus CD plus BD, and like, I'm supposed to memorize this crap. Well, it didn't make any sense. Why would you tell people that? Why would you make it that way? Why wouldn't you show them the algorithm of how to get there? As opposed to memorizing some dumb formula, which in the middle of the test, you're like, I forgot it. Well, you're screwed. If you memorize an algorithm, at least you're like, I get how to do the algorithm, I can probably get there. Or maybe at least fake it, I don't know. I hate trying to memorize something and then getting lost midway through and then like, now what do I put? Now what do I do? Seriously? Have I been talking for an hour and 25 minutes already? Wow. Time flies when you're having fun, huh, baby? Yeah, all right. Nice. All right, so I'll do another one kind of like that. Basically what I'm going to do is 3.2 today. In the process of doing 3.2, we're going to end up doing basically 3.3 as well. Okay, so 3.3 we'll put off till next week. Well, on Friday we'll cover 3.3, which puts us like one section ahead. Kind of, sort of, but not really. And so 3.3 won't be very hard to do. It'll all be about the imaginary solutions. We'll get into that a little bit harder next week, or on Friday rather. The test, I will pass the test out on Friday as well. So just be aware of that when we get there.
So how do you want us to do the homework? Do you want us to turn it in the day you pass up the test?
No, on the 20th.
Okay.
Yeah, let's do it on the 20th. Yeah, let's do that.
And have we established yet how much, like what we have to get through at that point?
Yeah, if you get up to like 3 point, let's say, yeah, if you get all the homework done up to like 3.1, 3.2, I'd be okay with that.
Okay.
Ish. Okay. Summer especially, I'm more mellow about it. Just get it done. Okay. But yeah, somewhere in that ballpark. All right, let's try this one here. This one should be kind of fun, I think. Why? Again, not going to do a lot of these in the real world scenarios in terms of the third orders. We do a lot of second orders. Oh my goodness, we do a lot of second orders. Third orders, But again, I run you through this step because I think it's kind of a big deal to understand the concepts. Once you understand the concepts, the rest of it's pretty much a piece of cake. Okay? Because it's just solving a quadratic equation again. That's right. Minus 5y double prime plus 8y prime plus, no, minus 4y. I lied to you. Minus 4y. Nice. Yes. All right. Again, the only way that happens is if you have e to the RTs. It's the only way that it's going to ever happen, right? That you could take the first, second, third, and fourth derivatives, add them up, and get to 0. The only way is if they're e to the sums, right? Of course, that encompasses cosines and sines, right? Because e to the whatevers and cosines and sines could also, well, sines and cosines are e to the whatevers. So this, right, via Euler's method, right? So e to the I theta is cosine theta plus I sine theta. So e's and sines and cosines go hand in hand. It's the only way we can make this work, okay? So, a couple things. That's the first thing that occurs to me. Thing number 2 is this guy here. is equal to 0. Again, because it's cubic, there will be 3 solutions. That does not mean they have to be all real. Okay? Yeah. Again, back in the not so good old days, we would have to check, hey, what are the factors of 4? 1, 2, and 4. And so you do plus or minus 1, plus or minus 2, plus or minus 4, and you guess and check until one of them might work. And if that worked, then you'd have a rational root, but there's no guarantee it's rational because you could have 2 irrational roots. Oh my word, what a mess. So, I'm just going to go ahead and graph this thing just for a good time. So what was it, r cubed? Then what was it? Minus 5r squared. And then it was plus 8r.
What number was this?
That's a modified version of 16. Oh, I hate you. What are you doing? Squared plus, there you go, 8x, add a bib. And then what did I say? Minus 4. Bam! Oh, that's hot. Whoa! What's that?
1 and 2, yeah.
Yeah. But how many solutions do I really have here? 3. Because this one is a single root, and this one we call a double root, right? When the vertex is on the line, it's a double root, yes? It counts twice. That's why when you say y equals x squared, there's 1, 0, it's at 0. But technically it's a double root, yes? Because the vertex is on the line right there. So it's a double root here, it's a single root here. Which means that if you had factored this, if you could factor this without doing anything else, you are a better person than I, friend. But this would have factored like so, and like so. So I would have got 2, 2, and 1. That's what r would have equaled. Uh-oh. What happens when you get a double root? We talked about this. You can't just do e to the t plus e to the 2t plus e to the 2t, because e to the 2t is the same answer twice, right?
Yep.
So what do you do when that happens? What's that?
You got to put another t.
Got to throw another t in there, right? So it's going to be, so y is going to equal c1 e to the t plus c2. I usually write it like this. You don't have to. You can jump right to the next step. I usually write it like that first. If you don't like that, you can jump right to here. Here is one solution. It's just the c2 e to the 2t plus c3 t e to the 2t. Yay! And our answer, there it is. Again, we need this to establish, this guy right here, to establish these as linearly independent solutions. All right? So what's keeping me from solving this? Well, I need to know some initial conditions. So y of 0 is 1. Y prime of 0 is 4. Y double prime at 0 is 0. Just for fun, when I look at this in a few minutes, I'm going to get a y-intercept of equal to 1, yes? When I get this done and graph it in a minute. It's going to have a slope of 4 at that point, yes? And it's going to be a point of inflection also, isn't it? It's going to be a point of inflection. Just going to keep that in mind when we get there in a minute, okay? So let's plug these values in. So when t is equal to 0, we're going to get c1 plus c2 plus nada, yes? So c1 plus c2 is equal to 1. From this top equation. Now, I'm going to show you how to speed this up on a calculator a little bit, because I don't know about you, but I got better things to do than try to sit here and take derivatives all day long. It's not that hard to do, but you'll end up screwing something up and you'll end up messing this up. So there's a kind of a quick way I like for this one, or these sorts of problems. So I still might solve the equation by hand, but for as far as taking derivatives and evaluating them, I think the easiest way to do them is this way. So take the derivative of Oh, before we do that, something good to get in practice of. Let's do this. If you take second, F6 right there, clear A to Z. If you don't do that first, things get ugly. Oh, they get ugly. We've just stored a bunch of stuff as A, B, and C, yes? So if I was going to use A, B, and C for my constants here in a minute, not so good. Not so good. So make sure you clear that first before you get too carried away. So I'm just going to do alpha A times, and then e to the t, plus, I'm going to do alpha b, that's my C2, e to the 2t, plus alpha c times t times e to the 2t. And we'll take the derivative with respect to t. So this mess comes out, and you're like, how is that more helpful? I don't know that it is yet. So this is why I like it so much. Come back and grab that answer and simply go such that button right here on the side, such that t equals 0, right? I'm just going to evaluate this baby at 0. And so I will get C1 plus 2C2 plus C1, or plus, well, you get my point. It's going to get C1 plus 2C2 plus C3 is equal to 4. In other words, take the derivative, evaluate it at 0, boom, pops right out. And then on the calculator again, I'm going to take the second derivative, so come back up here and just put a comma 2 at the end. Again, this is what the derivative is, and again, I don't care. I care about evaluating this at 0. So I grab it such that t equals 0, and I get C1 plus 4C2 plus 4C3 is equal to 0.
How did you get to C1 plus C2 equals 1?
That was from right here on the first one right here. If you plug 0 in for t right there.
Oh, okay.
That one I could probably do in my head, but the rest of them I get ugly. So I just think it's quick. Take a derivative. If your A's, B's, and C's are in there, bless you. If your A's, B's, and C's are in there, if you take the derivative and then evaluate it at t equals 0, what you're left with is constants. So that's what the constant is, and then equals whatever that initial condition was from above. To me, I just think that's easier. It's kind of a neat way of going about it. It speeds my life up. Now, if you can solve that by hand, good on you. I have better things to do. I don't want to. Okay? Your choice. I don't care if you use matrices. I don't care if you use a systems equation solver. I don't care if you do it. Back in my day, they never taught us how to do elimination back in the day. When I was in high school, it was all substitution. We had fractions on top of fractions on top of fractions. By the way, I got good at it, but looking back, I'm like, what a waste of my time. And then when I got to teaching, I was like doing that in elimination. What a waste of time. After a 2x2, what are you doing? So let's try this. If it's me, I'm going to do it on my calculator. I just find it very satisfying to solve them this way. So F2, solve. And then I'm just going to use x's and y's, but you can use C1, you can use C and B and whatever. So I'm going to do x plus y equals 1. And then remember, and, we need and is hiding several places. Actually, we technically need underscore and underscore. So if you get second, 5, 8, 8 is where it's hiding. It's also in the catalog, but you can do it any way you like. Second, 5, 8, 8. And then the next equation is x plus 2y plus z equals 4. Second, 5, 8, 8. And then x plus 4y plus 4z equals 0. Comma. Braces or squiggly brackets or whatever you call them. And then x comma y comma z. A friend of mine one time came to me and he's like, you know you don't have to do the squiggly, you don't have to do that on all the problems. And it's weird. The calculator will sometimes, if you just put comma x, it'll work. Sometimes it won't. And I can never find out why it does sometimes, it doesn't some other times, except it just piss me off, okay? There's a little person in there that hates me. And so if I don't put the squiggly brackets, it doesn't work half the time, so I always put the squiggly bracket. It always works if you include the braces, always.
Will that work using the reduced row echelon form matrix too?
You can totally do it that way too.
Okay.
Yes, good for you. Right on.
Well, that's just the way it got programmed into us in circuits.
Yeah, hey, it's whatever works. Yeah, if you want to use matrices, if you want to use matrix equation, if you want to use, reduced row, if you want to use augmented matrices and do it that way, there's about a million ways to solve this problem. Just find one that you're good with and go, okay? So we got, what do we get? Negative 12, 13, what was the other one? Negative 10. So negative 12 goes here, 13 goes here, and then you said negative 10? That would be my final answer. Hey, does that work? Let's find out, man. Let's go graph that baby and see what it looks like. So negative 12, e to the t? No, e to the, is that right? E to the x? And then plus 14, no 13. E to the 2x, and then minus 10x times e to the 2x. Oh, look at that. Does it cross where it's supposed to? It sure does. Does it have a slope of probably, could you buy that's a slope of 4? I'd buy that for a nickel. Does that look like it might be a point of inflection? I think so. So I'm comfortable in saying that, yeah, I find like that's probably my answer. That's probably my right solution. If it was going downhill, no, you screwed up. If it crossed at 5, no, you screwed up. If it was basically flatline, no, you screwed up. If there was no point of inflection there, I don't think so, pal. You messed up somewhere. These are the things that I always check when I'm done. It's an easy thing to graph it, see if it works. You don't have to go and find, I don't know, let's see what the actual derivative there is, and find out if it's 4 or not. It's not 1, it's positive, it's steeper than 1. I'd buy that it's 4, okay? That's just something that's really quick, really easy to check, okay? So, questions on this today at all? I apologize, I blew right through our non-breaks. We'll have a break at the end of class, and then you can go early, I guess. I'll hang out and answer some questions, but I think I've about talked out. That's pretty much, God, that was fast. Huh? Did you find it fast, or did you find it kind of like, is he still talking? Yes. Anyway, so that's kind of what you're doing in 3.3. So if you look at 3.2 as a learning tool, it's the idea that, okay, so what they put into it is that you're just using the determinant to see if they are linearly independent at first of it. Toward the end, they give you some solutions. They gave you these solutions. I factored them and found out what they were, okay? In reality, in that section, section 12 through 20 or whatever, they said, here are 3 solutions for this guy, okay? And in essence, number 1, are they linearly independent? And then 2, can you find the C1, the C2, and the C3 that would work for them? Yes, okay, it's the same exact thing. The difference being is I said, let's just run through this and let's actually find those solutions ourselves, okay? Which is what we'll be doing most of the rest of the book, to be honest with you, okay? So it's the idea of, just sitting here using a determinant to see if they're independent or not. Yes, it's important. You've done about 2 of those, okay, well, I can't really do much more with you, okay? But in reality, it's important to understand how that comes about and how it will always work through that deal. Also, I just want to point out to you that on page, where did it go? Oh, yes. I mentioned it last week, and on page 146, it talks about what happens if you have repeated roots. But it talks about it on page, where did it go? It's not the one. Because you can have more than 2 repeated. In other words, you could have a third one as well. And I was going to point that out, but maybe it's in section 3.3. Yes. Oh, it's in section 3.3. Yeah, in section 3.3, it talks about what would happen if you had more than 2. And so, what do you think would happen if my R equaled 1, 1, 1. What do you think my solution would look like? Just out of curiosity.
For which one?
T and T squared.
Yeah, it would be like C1 plus C2T plus C3T squared. Exactly right. Exactly right. Or if you prefer, I usually write it like this. If you want, you can certainly write it like this. But again, those three guys right there are all linearly independent. And so the next one would be t to the fourth and so on, or t to the third and t to the fourth and so on and so on and so forth. Okay? You barely see much of those because I don't do a whole bunch. I'm going to stick to pretty much second orders because second orders is mostly what you're going to see applied. This is the applied differential equations class. But again, once in a while you'll see something like this. Not to panic. That's what you do. Okay? So yeah, on Friday we're going to look at section 3.3. We'll do a bunch of examples, probably a couple of more or less applied problems, and we'll probably hint at something that we're going to be doing down the road. See if you can kind of like, oh, I bet it's one of those. Yes. Because it's very intuitive at that point, I hope. I think you'll start to see that it's, and I don't mean intuitive like the teacher doesn't want to talk about it, so he's going to say it's intuitive. I mean it's pretty dadgum intuitive. Once you see it, you're like, huh, yeah, I think so. Kind of like when we did that y double prime plus y prime plus y equals 0. It had to be e to the something. Right? Very intuitive like that. And so we're going to look at some of that on Friday, kind of foreshadow what is to come. You'll notice that I skip over the rest of chapter 3 and we move on. There's a reason for that because nobody does it that way anymore. At all, ever. Okay? Back in my day, which was not cool, you'd do a lot of guessing and checking and dinkle farting and hopefully get the right answer. And nowadays, everyone uses a system, for instance, like Laplace, to cut to the chase. Okay, so we'll come back and do those cool problems, but we'll do them with Laplace because there are hundreds of ways to do them. Not hundreds, there's a lot of ways to do them. Very much like solving a systems of equations. You do the one that works for you, but Laplace is a pretty good way to do that. So I will show you a couple of them that kind of like, oh, this is one way, but only because I think it's very intuitive. The other way is not intuitive at all. It is not even remotely intuitive. It's someone way more clever than I, sitting around the back room with a grease pen, maybe some marijuana, I don't know. Hey, this is a cool way to do it. How exciting. Listen, you have to self-medicate when you sit in the back room coming up with math problems all day. Okay, that would, whatever, I don't know. But I don't know. Hey, that's kind of a neat algorithm. And I guess it's kind of cool, I guess, but it's not one that we ever use in the real world anymore, okay? And it's not intuitive. So I'm glad someone found it out, and back in the day it was a cool tool. It's a cool tool from the past. Okay, we'll forget about that. Okay, so someday when you get a PhD and you want to like write your dissertation about it, go for it. But the rest of us aren't going to do it that way. All right, I'm done talking.